In 1924, an unknown young physicist, Louis de Broglie, published an article in the Philosophical magazine about the principal points of his PhD dissertation, which was devoted to the possible existence of matter waves. His views was completely unorthodox and paradoxical. He argued that waves are generated in the motion of any body, whether a planet, a stone, a particle of dust, or an electron, it doesn't matter. Like electromagnetic waves, they are capable of propagation in an absolute void. Hence, they are not mechanical waves. They are produced in the motion of all bodies, including those not charged electrically. Hence, they are not electromagnetic waves. At that time, physicists did not know of any other kinds of waves than mechanical or electromagnetic waves. So, de Broglie's matter wave concept was some kind of nonsense to most of the physicists. However, existence of matter wave was experimentally demonstrated by 1927. De Broglie obtained a relationship connecting the wavelength of matter wave with the mass and velocity of moving bodies, which was lambda equal to h by mv, where m is the mass and v is the velocity of the body and h is the Planck's constant. As you can see, this equation encompasses both the wave nature and the particle nature of an object. Classically, a particle is considered to have a definite momentum, whereas a wave has a wavelength. In classical view, waves doesn't have any momentum or particles doesn't have any wave nature. But de Broglie's equation has or it connects these two things. It says that moving objects has waves as well as particle character. Since h is a minute quantity, this equation suggests that the associated wavelength of moving bodies are extremely small. So let's try to calculate it for the planet Earth. Earth has a mass of 6 into 10 raised to 24 kilogram and its orbital velocity can be approximated as 3 into 10 raised to 4 meter per second. Putting these values in the de Broglie relation says that it has a wavelength of 3.6 into 10 raised to minus 63 meter. As you can see, this is an insignificantly small quantity and no instruments could ever measure this value. There just doesn't seem to be any comparison to illustrate how small this figure is. Now let's take the case of an electron. It has a mass of about 9 into 10 raised to minus 31 kilogram. If the electron is moving in an electric field with a potential difference of 1 volt, it will acquire a velocity of 6 into 10 to the power 5 meter per second. Putting these values in de Broglie relation says that moving electron has a wavelength of 10 to the power minus 9 meter. This is approximately the wavelength of X-rays, which can be easily measured. So in principle, we should be able to detect de Broglie electron waves. Now you can see that even though all kinds of moving bodies have waves associated with it, the wavelength is measurable or detectable only when the particle size is very small. So for the case of our normal objects or the objects which are quite big enough, the wavelength is not noticeable as its wavelength is extremely small. But as we go to minute particles, subatomic particles, then the wavelength associated with such particles are very much measurable and they are not negligible. The momentum of relativistic particles, that is when its speed approaches the speed of light, is given by the expression P is equal to gamma mv, where gamma is given by 1 by square root of 1 minus v square by c square. V is the particle velocity and c is the speed of light. So de Broglie relation for relativistic particle is given by the expression lambda equal to h by p, and in place of p, if you use relativistic relation, we get h by gamma mv. As in the case of waves, the waves and particle aspects of moving bodies cannot be observed simultaneously. In certain situations, it resembles a wave, and in other, it resembles a particle. Wave nature of moving objects become more evident when its wavelength is comparable with the dimension of the object itself and also the dimension of whatever with which it interacts. So we have seen that the wavelength associated with most of the moving bodies are too insignificant. Thus, even though de Broglie wave exists in theory, there doesn't seem to be a way of detecting it instrumentally. But as you know, a wave is a wave and there must be some phenomenon in which it will manifest itself no matter what its nature. Since diffraction is a completely wave phenomenon, an attempt was made by scientists to catch the de Broglie wave in diffraction experiments. In diffraction experiments, we have another problem. The dimension of the obstacles used to observe diffraction of a wave must be comparable with or less than that of the wavelength itself. So, even with the case of a moving electron, as we have seen in the example, the size of the diffracting object must be of the order of nanometer or angstrom. In 1912, the German scientist Loewe noticed the diffraction of X-rays on crystals. He noticed a series of dark and bright dots on a photographic plate exposed to X-ray that had passed through a crystal. In this case, diffraction was possible because the distance between the atoms in the crystals were of the same order of magnitude as the wavelength of X-rays. Wavelength of electrons are also in this range, which means that if these waves do really exist, then electrons in passing through a crystal should produce same diffraction pattern as X-rays. A few years after de Broglie introduced his concept, the American scientists Davison and Germer verified the existence of de Broglie waves on diffraction of electrons by crystals. In the Davison-Germer diffraction experiment, they studied a surface of nickel. Experimental setup is shown here. The thermal electrons are released from a heated element in the electron gun and accelerated through a potential difference delta V, and it becomes a well collimated beam of electrons. The kinetic energy of the electron is adjusted by adjusting the potential difference in the electron gun. This produces a beam of electrons with a set value of linear momentum in accordance with the conservation of energy. The electron beam is incident on the nickel sample in the direction normal to its surface. At the surface, it scatters in various directions. The intensity of the beam scattered in a selected direction phi measured by a highly sensitive detector. The detector's angular position with respect to the direction of the incident beam can be varied from phi equal to 0 degree to 90 degree. The entire setup is enclosed in a vacuum chamber to prevent electron collisions with air molecules, as such thermal collisions would change the electron's kinetic energy. According to classical physics, the scattered electrons will emerge in all directions of scattering angle, and it was what Davison and Germer observed in their experiment. But during the experiment, some accident happened which caused air to enter the chamber and oxidized the nickel target. To reduce the oxide to pure nickel, the sample was heated in a high temperature oven. After heat treatment, they put the target back into the experimental setup and resumed the experiment. Now the results were very different from the previous case. Instead of continuous variation of scattered electron intensity with angle, they observed distinct maxima and minima. The intensity of the scattered electron beam showed clear maximum at some specific angle. That is, the result showed a clear diffraction pattern like this for the accelerating potential in the electron gun of about 54 volt. Similar kind of diffraction pattern were known to the physicists of that time, as they have seen many such kind of diffractions by the X-rays scattered by various crystalline solids. The polar graph of electrons intensity is shown here. In this polar plot, the intensity at an angle is proportional to the distance of the curve at that angle from the point of scattering. So what is the reason for this new effect? These observations suggest that, as de Broglie suggested, the electrons' waves were being diffracted by the target in the same way as X-rays are diffracted by Bragg reflection from crystal planes. Then why did it not appear until the nickel target was baked? It was realized that the effect of heating a block of nickel at high temperature caused many small individual crystals of which it was composed to form into a single large crystal. That is, all of these atoms got arranged in a regular lattice as a consequence of heating. Hence, heat-treated nickel act as a single crystal with interplanar spacing sufficient to scatter electron waves. The maximum intensity was observed at an angle of 50 degree from incident electron beam direction. With respect to the family of Bragg planes, this corresponds to an angle of incidence and scattering both 65 degree. From X-ray diffraction, they found that the spacing of the planes in the nickel crystal was 0.91 angstrom. The Bragg equation for maxima in diffraction pattern is given by n lambda equal to 2d sine theta. Assuming first order diffraction, for which n is equal to 1, we can calculate the wavelength of the electron from the known values of interplanar spacing and angle of incidence. It gives us, after substituting these values, a wavelength of 1.65 angstrom. Now let's use de Broglie formula to calculate the wavelength of the electrons. Formula is given by h by p, and if you substitute for p in terms of the kinetic energy of the electrons acquired by the applied voltage, we have an expression lambda equal to h by square root of 2me delta v. Substituting the various parameters in de Broglie equation, we get exactly the same value as suggested by Bragg's law. Thus, Davison and Germer experiment does provide the direct verification of de Broglie hypothesis of the wave nature of moving bodies. So this resemblance shows that electron in this particular example behaves like a wave which produced an kind of diffraction effect as suggested by or as observed in the case of X-rays scattered by crystals. In Compton experiment, we have seen that light, which was believed to be electromagnetic waves, shows particle nature of definite momentum. In Davison-Germer experiment, we have seen that electron, which was believed as particles, shows its wave nature. If electron has wave properties, then all objects of our world from the smallest to the biggest must be having the properties of waves. There were several other groundbreaking discoveries and experimental demonstrations which indicated the wave nature of classical particles and the particle nature of classical waves. By the first quarter of 20th century, the wave-particle duality became a well-accepted concept, and de Broglie was awarded Nobel Prize in Physics in 1929, and Thomson and Davison shared the Nobel Prize for Physics in 1937 for their experimental work. Wave-particle duality rejects the classical concepts of identifying something like a particle or wave alone. For the case of photons, Einstein wrote like this: "It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomenon of light, but together they do." So this statement was originally given for the case of light, for which he suggested both the particle nature and the wave nature. But at that time, it was also clear that the matter itself has wave nature along with its particle nature. So this wave particle duality became an accepted or well accepted concept by around 1930.